Hey, welcome back to Math with Patrick and Quill. Today is June 28th, and we're solving problem number 179 from the Daily Epsilon calendar. And we need to show why this area of the blue triangle is going to be 28 times the square root of 3. So I'm assuming that this line right here is a diameter of a circle. It just kind of looks that way. It looks like we're going through the center of the circle, and it looks like it's going, all the way across from edge to edge. So I think I can assume that is the diameter. That does let me assume that this angle measurement on this straight line essentially is 180 degrees. And then I can use the central angle theorem to figure out that this angle right here is actually a 90-degree angle. In fact, anytime that you have a triangle where the 3 points that make up the triangle are, two of them are part of the diameter and a third is anywhere else on the circle, it's always going to form a right angle here. So even if I moved this point over here and I drew this triangle, this is always going to be a right angle. And I can back it up with the central angle theorem. So I'll mark a right angle right there. I'll also mark the center of the circle just so I have something to work with. And to find the area of a triangle, I'd really like to just be able to do base times height and then divide it by 2. And I'm pretty sure these are not supposed to be intersecting, right? Because maybe if this right angle were somewhere over here, clearly that's not going to be in the center of the circle. So this altitude of my blue triangle doesn't have to, and it probably won't intersect the center of my circle. Anyways, area is 1/2 times base times height. The base is just going to be this length right here. 4 plus 10 is 14. And so if I just get that h, I'm basically all set. The area of the triangle is going to be x root 3 right here. So once I find h, I'm done. I'll mark it on the diagram right there. Now it's easier said than done, though. The best way that I have to solve this one is to create more variable names for things that could be different lengths, and then use a system of equations to kind of nail down each one. So I'm kind of thinking about that idea of moving this point maybe left or right. And so if I move this point over this way, this diagonal could be a different length. Same thing with this one. And so I do want to mark them with variables. I think I'll just call them A and B. And I haven't really talked about this length here of 8 just yet. To me, it seems almost out of place. I don't know what any of these angles are near this line segment. I'm not really sure if it should land, over here or over there. I don't know which way this 8 should be located. I know it's kind of a little bit to the left of the height or the altitude of my blue triangle, but I'm not sure how far away it is. And so I'm going to mark this distance right here with another variable. I'll just call it m. I'll also label some 90-degree angles here because the altitude of a triangle is always perpendicular to its base. But I'm not really sure how far away this kind of diagonal length goes, and so that's why I have yet another variable m in my diagram. So there's a, b, h, and m, and ultimately I really want to find h. And there's 4 unknowns. With systems of equations, you need the same number of equations as unknowns to have any hope for solving for the values. So with 4 unknowns, there's m, h, a, and b. I really want to have 4 equations to kind of compare them all. And the equations need to come from different sources. Fortunately, we have a whole bunch of right triangles in this diagram, so I'm going to do a whole bunch of Pythagorean theorems to try to line up all the variables with each other. So I'll start with this right triangle on the right side of the diagram. My base will be a little bit strange. It's going to be this length right here, and I really want to use just these 4 variables. I don't want to create a new one. This length right here was a 10 from the problem statement. So if I take 10 and subtract away my m, I'm going to get my base length right there. So 10 minus m squared plus h squared is equal to b squared. So that's one Pythagorean theorem down. Let's do maybe this triangle over on the left side of the diagram. Looks like my base is going to be 4 plus m. Square that because of the Pythagorean theorem. H squared is going to be like the other side, and then both of those added together will be a squared. A right here is my hypotenuse. I do have the big right triangle, the whole triangle that I'm actually trying to solve for its area right now, the blue one. The legs are going to be a and b. So I'll do a squared plus b squared. And then c squared is going to be this hypotenuse squared. And I can get the length by adding the 4 and the 10. So I'll just write it as 14 squared for now. I know that's 196, but why not? Everything's being squared right now, so might as well keep it in a similar format. The last right triangle is this one in the middle. That 8 is the hypotenuse, so I'll put 8 squared over here. And then its legs are going to be h and m. So I'm going to do, how about h squared plus, oh, you know what? Let me do m squared plus h squared. The only reason why I'm doing it this way is because all of my other equations have h as that second variable. So I kind of like how it matches all the other ones. And overall, I really want to know the h variable. Like, it'd be great to know a, b, and m as well, but ultimately h is the important one, just because that's the height of the blue triangle, and that's what I need to use for the area. So hopefully there's a way to kind of condense this system of equations down where I'm just solving for h. I'm noticing this equation relates h and m, and so maybe if I get rid of the m's here and here, I'll just have h's up top. And then this equation, since it'll just have a b and some h's over there, I'll be able to sub out the b in this equation. And similarly, I could sub out the a squared here. And so that's kind of my plan. I want to make them all talk to each other, and ultimately this will be the last equation that I use, and I'm hoping that I can get just h's on this side. And I'll solve for h, I'll get the height, and it'll be great from there. So how about, actually, let me expand these two. There's also something that I'm noticing in these ones. If I expand that first binomial, I'll get 10 squared minus 20m plus m squared. Then the plus h squared equals b squared is already like part of the equation. So I'll expand out the second one. That's going to be 4 squared plus 8m plus m squared, and then plus h squared equals a squared. That part was already there as well. And then I noticed the reason why I expanded this is that m squared plus h squared is just the same as 8 squared, or 64. So maybe it'll actually be nice for me to start figuring out what these numbers are squared. And so I'll replace both of these with 64s. So 64, 64, that equals b squared, that equals a squared. And then how about I'll expand this part out too. That's 100 minus 20m plus 64, 16 plus 8m plus 64. There we go. And I know I could kind of condense these a bit more, but I'm feeling like I want to shove them both in this equation now, where a squared is just the same as 64 plus 16 plus 8m, and then b squared is the same thing as, 100 minus 20m plus 64. And then all of that equals 196. So I know my original plan was solving for h, but it looks like the easiest thing that I found was solving for m. And that shouldn't be that bad because h and m together are like really closely related. Maybe I'll have to do one more Pythagorean theorem at the end. Let's just solve for m. All right, combining my like terms, these two together are going to create a negative 12m. I can cross those off. Then I have 64, 64, 16, and 100. And I'll keep the 196 on this side for now. 64 and 64 make 128. Adding on the 100 is a 228. And then adding on the 16, I'm sure I could probably do this in my head, but I think 244 looks right. I just wanted to kind of write it all out to make sure that I was doing it right. Okay. So 244, minus 12m equals 196. I think I'll just do more algebra steps. So I'll subtract the 196 from both sides, and I'll add the 12m over to the right. So figuring out the subtraction, I guess I'll do some borrowing. Give me just a sec. Looks like that's 48. Ah, cool. And so m turns out to be a whole number. M is just 4. So let's see what that means for our triangle. M right here is equal to 4. Oh, so kind of interestingly, this diagonal that I couldn't place earlier just happens to be halfway between the altitude and the edge. So that's a kind of convenient spot for it. But more importantly, we now have this middle right triangle that we can use to solve for h. The base is 4. The height, h, still don't know it. The hypotenuse is 8. So when we Pythagorean theorem this guy, we get 8 squared minus 4 squared equals h squared. On the left-hand side, we got 64 minus 16. That is going to be 48. Interesting how 48 showed up again. And so the height of our triangle, or the altitude, is the square root of 48. We could simplify that a touch. I know that I could rewrite this as root 16 times root 3. You're totally allowed to split up radicals like this as long as they're being multiplied. And then to simplify the square root of 16, h is going to be 4 root 3. Great, let's bring that back up into here, where I'll just replace the h with a 4 times root 3. And then I'm noticing that if I wanted to kind of simplify both sides of the equation, I could divide both sides by the square root of 3, and then maybe I could combine these to be a 2. And so ultimately, we get x is equal to 2 times 14, which is 28. And that's today's date. There we go. So maybe there's a better way to solve it besides making a long list of equations. This is the best way that I could solve it, finding a system of 4 equations and 4 unknowns, finally nailing down one of them, and then using that information to solve for the one that we really wanted, which was h today. So the area is 28. That's my solution, and I'll see you tomorrow. Bye.